Alright, fourth part of our related rates, and I'm still unsure as to how many of these videos I'm going to do for related rates. I may stop after 5 and then do more if you specifically request it. So let's go ahead and get started. Here's another classic one that I want to show you. Okay. And this one pops up in every single textbook. A boat is being pulled into a dock, attached to it, and passing through a pulley on the dock, positioned 6 meters higher than the boat. Okay, so all that's saying is a boat's being pulled into the dock, a rope is tied to, so let's say, the front of the boat, and the rope is being pulled through a pulley. Now, usually the deck is going to be just a little bit higher than the boat. In this case, the deck is 6 meters higher than the boat. Okay, does that make sense? Now, if the boat is being pulled in at 3 meters per second, how fast is the boat approaching the dock when it is 8 meters from the dock? Okay. Now, here's generally what's happening. Okay. This is what's happening. Okay. Pause. And this is, remember, always go and look at Wolfram demonstration, especially when there's motion involved, because a lot of calculus teachers put lots of neat stuff up there. This is what's happening. Now, this is not exactly the scenario that we have, but this is generally what's going on. Now, this portion right here, the hypotenuse is the rope, right? This is that 6 meters right here, and this is the dashed line is the lateral distance from the boat to the dock. Okay, so now that we've sort of gotten a visual of it, let's go back and draw our own picture. Now, we know that we have a cute little boat. Oh, isn't that cute? Okay, now we happen to know that there is a dock. That dock is 6 meters higher. Okay, and it's going to smudge a little bit. It's the only problem with these gel pens. Okay, now we've noticed, actually that's a solid line, that's not that. So we've noticed that it's another right triangle, right? Because that imaginary lateral distance right there creates it. Now, here's the water, but I'm not really worried about that. I'm worried about the fact that that right there is 6 meters higher, okay? We'll call this distance right here x, since we're used to. Let's call this z, okay? Now, let's talk about the information that's given to us, okay? If the rope is being pulled in at a rate, okay, so first of all, the first given piece of information is already in my thing right here. It's y is equal to 6 meters. But I also have the rope being pulled in at a rate of 3 meters per second, okay? That is the change of the hypotenuse right here, okay? That is dz dt. And remember, because it's being pulled in, it's making z shorter, so it's negative 3 meters per second. So that's my given information. Now, okay, and notice that that when right here tells me about this piece of information. That's obviously conditional. The question is, how fast is the boat approaching the dock? What is my dx dt? How fast is this distance shrinking? We should expect dx dt to be negative, okay? So we need to look out for that. My conditional information is, of course, when x is 8, okay? Well, I tell you what. When x is 8, if this is 6, z is 10. That's my implied conditional, okay? So I have, and I know I'm going to need that. And so what I have here is x squared plus 6 squared is equal to z squared. And as I differentiate, I'm going to go ahead and get rid of the coefficients of 2, since I know they're going to cancel out. Well, I won't. I'll go ahead and cancel them out explicitly for you. Dx dt plus 0 is equal to 2z dz dt. And I know that that 0 doesn't matter. That 2 is going to cancel out with that 2. And what I'm looking for is dx dt. Now, if I want to go ahead and solve for dx dt before I do my plugging in, that's just fine. Okay? Now I happen to know that z is 10, okay? X is 8, and it's nice that those are right on top of each other because it shows that the units are going to cancel out. And then dz dt is negative 3 meters per second. Now this winds up being 5/4, so it winds up being negative 15/4 meters per second. And that should be the rate at which it's being pulled in, okay? So this is how fast the rope is being pulled in. This right here is how fast the boat is being pulled in. This is close to 4. This is 3, okay? Now, but did you notice back in the animation that the speed at which it's getting pulled in is pretty constant, but then it increases right at the very end, okay? Just because of the nature, the quadratic nature of the relationship between the sides and how that impacts the rate, okay? Let's go ahead and move on to the next problem that we're going to do. And this one is a pretty standard one as well. It winds up being rather straightforward, and it's one kind of like what we've already seen. Assume that sand allowed to pour onto a level surface will form a pile in the shape of a cone. So let's say you have a conveyor belt and sand is coming off the conveyor belt at a constant rate and it's pouring on the ground. Well, you know, it's not going to pour straight up in terms of just a stack of sand. Some of that sand is going to slide down. It's eventually going to wind up making a conical pile, okay? Now, with the height equal to the diameter of the base. Now that right there is an incredibly important phrase, okay? Now, if the sand is poured at 2 cubic meters per second, well, let's go ahead and, you know, draw this, you know, and here's the conveyor belt, you know, and it's being poured on, okay? If the sand is being poured at 2 cubic meters per second, okay? Now, sometimes if tells me that's conditional. In this case, that's not conditional. That's actually constant, okay? So sometimes if is a little bit ambiguous as to whether it's conditional or given information. That right there is given information. So you know that dV dt, and since sand is being poured on, the volume is increasing. That's a positive 2 meters cubed per second. How fast is the height of the pile increasing? What is dH dt? When the base, and there's your conditional piece of information, when the base is 8 meters in diameter. Well, I don't usually deal with diameter. I usually deal with radius. So if the diameter is 8, the radius is 4, right? Now that's helpful because I know that the volume is pi over 3 r squared h, okay? Well, here's the thing. That right there, and this is not a perfect picture, obviously, that's R and that's H, okay? Now, I was told, if you remember, that diameter is equal to height. Well, that tells me that 2 times the radius is equal to height, okay? So if 2 times the radius is equal to height, then radius is equal to height over 2. And that gives me something that I can plug in for r over here, okay, in order to turn this in from a equation of 3 variables into an equation of 2 variables. So v is equal to pi over 3 h over 2 squared times h, which gives me pi over 12 h cubed. So if I differentiate this with respect to time, I'm going to get pi over 4 h squared dh dt. Well, that's all well and good, except for the conditional information that I was given was r. But the implied conditional information was the fact that h was equal to 8 meters, right? That's the implied conditional because I have this conversion ratio. Plug 4 into here, multiply by 2, and that is h, okay? So that means my dv dt is pi over 4 times 8 meters squared times 2, no. Sorry, that was actually dh dt, and that should be equal to dv dt, which is 2 meters cubed per second. So I flipped the equation around, but it's the same thing, right? This went here, and this went here, but it's the same thing. Now, the only thing that I really have to do now is know that dh dt is 2. Now, this right here is going to simplify into, well, that's going to be 64 meters squared. So 64 divided by 4 is 16. So that's going to be 16 pi meters squared, okay? And so I'm going to get 2 meters cubed over second over 16 pi meters squared, and that's 1 over 8 pi meters per second. And that should be the rate at which the height is increasing on that pile, okay? And it's positive because the height should be increasing when the volume is increasing. So that makes perfect sense for us. Now, I don't have much time to go through an entire another example, but I am going to show you a question that I asked the BC kids, was it last year? I think so. This was on their test. A cylinder has a radius of 4 centimeters and a height of 6 centimeters. The radius of the top, and not both bases, just the top, is decreasing at a rate of 0.1 centimeters per second. Okay? This means that the cylinder is slowly becoming a cone. So just think about a cylinder. The bottom base stays the same, but the circle which forms the top base is shrinking from a circle down to a point. Okay? And it's doing so as the radius shrinks or decreases by 1/10 of a centimeter per second. Is the volume changing faster at the beginning or the end? That's a typo right there. It should say or the end of the process. Justify your answer. Well, I told them, okay, so it has to pass through being a frustum first, and that's a frustum, and here's the frustum of a right circular cone, and that's the volume. And you're looking at that and you think to yourself, oh my gosh, that is the most ridiculous thing. How in the world am I going to do this? But remember, what we need to ask ourselves is, what is changing? What's changing? Because here's the thing. If only the radius of the top is changing, is the height changing? And the answer is no. Is the big radius changing? And the answer is no. Okay? So what I was looking for was a recognition of what was changing and what was not. Okay? Now, what I'm going to do is I'm going to turn this around, this part in the parentheses, and I'm going to acknowledge the fact that the only things that are changing are this and that. Okay? Everything else, for our purposes, is a constant and is therefore part of the coefficient of small r. And therefore I can sort of put it in terms of a quadratic, right? Where everything in parentheses is constant with respect to the scenario that I've been given. And therefore dv dt is going to be 2 pi h over 3 r times dr dt plus pi h r over 3 dr dt. Well, I happen to know that not only is everything in parentheses a constant, dr dt is a constant. Okay? So when is dv dt going to be at its maximum in terms of magnitude? Well, the only thing that's changing here is r. So dv dt is largest when r is largest. And therefore, what we have is, and you can go ahead and pull out the pi h over 3 times dr dt out of both terms, and you're left with 2r plus r, right? So all of this is largest when this small r is largest, and therefore it is going to be when this is at its beginning, when it's still a cylinder, the moment that it starts to collapse into a cone through the frustum shape, it's going to be changing faster at the beginning. Okay. I'm gonna go ahead and do one more video, like I said, and these are going to be a little bit more robust in terms of what they require us to remember and sort of thinking through the stuff, largely because there's trig involved. So you have that to look forward to. Yeah, I think that pretty much brings us to the close of all of the classic related rate problems that you're likely to see either on a test or on the AP exam. But we can go through more. But I need to basically finish off the 3.9 stuff and get on to doing a couple of videos for linear approximation in 310. So look for video 5 and then look for videos for linear approximation.